Historically, building interfaces in this CMS meant navigating severe architectural fragmentation. The system relied on 4 completely disconnected methods for rendering reusable content, with each operating entirely in its own silo. This lack of a unified component model created massive technical debt across the codebase. Developers were forced to duplicate core infrastructure, writing redundant caching mechanisms and template resolvers for every individual output type. The primary bottleneck lived in the legacy block system. These were procedural UI components heavily reliant on global state, managed through massive centralized administration files, some stretching to nearly 600 lines of code just to handle basic operations. Configuration within these blocks relied on untyped, pipe-separated strings instead of structured data. Passing parameters as raw text streams bypasses type safety entirely, making proper data validation and automated testing nearly impossible. Architecturally, these procedural blocks were built with hard-coded assumptions about where and how they would be displayed. This strict coupling prevents them from supporting modern engineering requirements, like headless API delivery or nesting components inside one another. Legacy CMS models fail under modern constraints because they inextricably entangle the act of fetching data from the database with the process of rendering HTML. You cannot extract the data without also extracting the markup. The architectural solution to this procedural debt is the XMF 2.0 Unified Widget System. The entire system is built on a single, uncompromising rule: interface-driven design. The widget interface enforces a strict separation of concerns between raw data and presentation logic. Under this interface, the component class has a single responsibility: execute the getData method and return a raw array. It knows nothing about templates or HTML. Complex infrastructure logic, caching, permissions, events, and templates is entirely offloaded to a centralized rendering pipeline. To eliminate the massive administration files, the system introduces PHP 8.4 declarative attributes. Manual procedural component registration is replaced entirely. By simply adding the hash widget attribute above a class definition, the framework automatically discovers, indexes, and maps the component at boot time. The developer writes zero plumbing code to connect the component to the system. Combining a single data fetching interface with declarative metadata yields a zero boilerplate environment. Developers write a 30-line class focused strictly on business logic, and the framework handles the rest. A classic engineering problem in CMS architecture is the conflict between 2 distinct user bases: back-end module developers who write PHP and front-end theme designers who write HTML and CSS. In this unified model, back-end developers build components using compact PHP classes with attributes. Front-end designers construct components through declarative JSON manifests, requiring no PHP. The framework resolves this split during ingestion, parsing both simultaneously to output a single, immutable widget definition object, standardizing the format. Once the component reaches this compiled state, the underlying rendering engine cannot distinguish between a PHP origin component and a JSON origin component. They execute through the exact same lifecycle. Unifying these disparate creation paths into a single metadata object eliminates the need to maintain fragile compatibility bridges, legacy adapters, or separate rendering loops for themes and modules. Every single component request in the framework, whether called from a template, a REST API, or an article shortcode, is processed by a central orchestrator called the widget renderer. When a render request fires, incoming configuration data hits the pipeline's first major gate, property hydration. Here, the @prop attribute enforces typed validated schemas. It rejects invalid data types, like a string instead of an integer, applying correct defaults before the component sees the data. Because this schema is strongly typed, the framework uses it to automatically generate the administration UI, building forms natively without manual HTML. The data then moves to the next crucial gate, the visibility and permissions check. The hash widget visibility attribute evaluates user permissions against compiled metadata before instantiation, conserving memory. If a check fails, the system doesn't throw a blocking error. It gracefully returns an empty object, diverting to a clean exit path and bypassing the rest of the pipeline. Shifting configuration validation and access control strictly to the attribute layer secures the execution environment before any actual rendering begins. The component only runs when it is safe, valid, and authorized. Running a highly dynamic, multivariant component system at scale presents a severe database performance challenge. Querying multiple data components per page load requires aggressive caching. The pipeline's caching gate uses a formula to guarantee unique state, constructing a cache key from the component's name, its variant, and a final calculated block. That segment is an MD5 hash, cryptographically condensing the sorted properties into a unique, fixed-size string. Hashing the exact configuration properties prevents cache collisions. A recent post list configured to show 5 items generates a completely different hash and a different cache entry than the exact same list configured to show 10. But aggressive caching introduces a secondary challenge: the risk of serving stale content to users when the underlying database records change. The system solves this with a tag-based instant invalidation mechanism routed entirely through the framework's internal event bus. When a domain event fires, like publishing a post, it travels the bus, reads the metadata, and instantly wipes all cache nodes bearing the corresponding hash widget cache tag attribute. Tightly coupling the component cache to the system's event bus eliminates the reliance on arbitrary time-to-live guessing. The cache holds indefinitely until the exact moment the data changes, guaranteeing absolute consistency. Because the rendering logic is detached from the data logic, components can utilize composition. They can be nested inside layout nodes to form an abstract syntax tree, or AST, a hierarchical tree structure representing the final page layout. This tree architecture allows developers to construct complex, multi-layered page sections entirely on the server side, passing properties down from parent nodes to child components. Deeply nested architectures carry a stability risk. If one child node fails a query, it threatens a cascading failure that breaks the parent structure. To prevent this, the framework enforces an error boundary. The failed node simply returns an empty string. Isolating execution failures to empty outputs guarantees that a single broken data query will never compromise the structural integrity of the surrounding page layout. The page continues to load around the missing element. The final step of the pipeline condenses the HTML, the required CSS and JavaScript assets, and the metadata into a standardized rendered widget value object. This finalized object can then be pushed down 3 distinct consumption paths: injected into server-side templates, parsed into text articles via shortcodes, or delivered as JSON payloads through headless REST endpoints. The strict architectural decoupling of data from HTML makes this multi-context delivery possible. The data is fetched once, and the pipeline routes it to any output format without requiring the developer to write secondary routing logic. This routing flexibility enables the ultimate developer experience feature built into the system, the @widget lazy attribute. Applying this single attribute automatically converts a heavy server-side render into an asynchronous AJAX request, a background network call that fetches data without halting the browser. The pipeline drops a temporary placeholder on the screen, letting the page load instantly while the complex component renders in the background. The XMF 2.0 architecture proves that enforcing declarative, interface-driven design is the definitive way to achieve high-performance, headless-ready composability, while keeping the developer experience focused entirely on the logic that matters.